Hey everybody, we are finishing up. I am on the last page of the supplemental notes, page 19. And if you're interested, at the end of the video, I will just briefly discuss these exponent properties. Really important to know, but not something that we focus on too much right now. Where I am going to bring my focus, though, is down here where we still have a radical that's in the denominator, but it's accompanied with another term. And since there's two terms, we call that a binomial. And what I need for you to remember, what I've said in the previous video, is that denominators are really picky. They don't like radicals in the denominator. And in the other section, 3.5 with those imaginary numbers, they don't like imaginary numbers in the denominator. So you have to do some work to get rid of those radicals that are in the denominator or those imaginary numbers that are in the denominator. And so in our last section, if you had a problem like this, then the I in the numerator is fine, but the I in the denominator they don't care for. And so to get rid of that, you would have multiplied by its conjugate. And if the original denominator is 7 minus I, then its conjugate is 7 plus I. And then you could go through this multiplying of your numerators and then the multiplying of your denominators, and you would have seen that all the I's in the denominator would have disappeared. All right? So what I want you to see now are these other conjugates that exist. So let's just go back and take care of what we had before. So the one that you're already familiar with back from chapter 2 is a difference of squares. So the idea is a plus b and a minus b are conjugates of each other because one set of parentheses, one factor has a plus and the other one has a minus. And so what I'm going to do is multiply these conjugates and just show you what happens. So first I'm going to have a distribute into the other parentheses. My students know this as the neighbors meet the neighbors, and I get a squared minus ab. And then I'm going to have the b distribute or meet the neighbors, and I'm going to get another ba or ab, and I like to stack my like terms. And then the b's will multiply or distribute. I'm going to get minus b squared. And what happens is these middle terms, these ab's cancel out, so that when we're done, we have a squared minus this whole b squared part. Then in imaginary numbers, we did this again. This was our last section, and we talked about the conjugates. And these are just general letters. So again, I'm going to multiply. I'm going to get a and a, so there's a squared. A will distribute or multiply to this. I'm going to get minus a with b and I. And then the bi distributes or meets the neighbors, and I'm going to get a positive version of all of that. And then finally, the last terms meet or distribute or multiply, whatever you want to say, and you get minus, and then bi times bi, that would be, so I'm going to erase this just a moment. Bi times bi, you could write as b squared I squared, but I'm just going to write it as the whole thing is squared. All right, so I'm going to put that here, and I'm going to put it in parentheses. Oops, I'm writing an a though, as that happening. All right, and so again, what would happen is these would cancel out and you would get a squared minus, and then I do need to keep it in parentheses so that you realize that all of it's squared. You get that. And that's supposed to be a minus sign. Not very good. Now in this chapter, or sorry, this section, we're talking about conjugates that have radicals, and radicals represent an irrational number, a number that if you did turn it into a decimal would not be a very nice decimal. So let's look at what happens here. So we're going to start with the a's multiplying, distributing, and I'm going to get a squared minus a with b still inside that square root, and now the square root of b is going to multiply, and I'm going to get a positive a with b inside a square root. And then when I multiply those, again over here, anything times itself like that, I could just write, since it's multiplying twice, I'm going to write it as squared. So I just want you to be aware of where I'm getting that. So minus, and I have to put it in parentheses to show that it's all squaring. And these, just like everything else, is canceled out. And when we're done, we get this. And so what do we want you to notice over here? So first, we want you to notice that we have two terms that always cancel out. And then the other thing that I want you to notice is that what is left is something squared minus something squared on all of them. And if you take a look at what those things are squared, if you just looked at one of your parentheses, one of the sets of the conjugates, well, that did not highlight very well. The A is being squared and the B is being squared, or the first term is being squared and the last term is being squared, and it's always hooked with the subtraction. And that happens here. The first term, A, is being squared. I should have put that in parentheses. And then the BI, well, that's all being squared, hooked together with subtraction. And then the A is being squared. That should be in parentheses as well. The square root of B is being squared, and it's hooked in subtraction. So let me put those in parentheses real quick. So the overall idea is that if you just look at one parentheses, it's the first term that's being squared, and then the last term that's being squared, always hooked together by subtraction. So we're going to use that idea, and let's go into this problem down here. So I don't have as much room, but I'm going to rewrite it. And the problem that I'm running into here is that I have a radical, and denominators do not like radicals, but because there's two things, to get rid of that radical, we're going to use this denominator's conjugate. So if we start with 3 plus the square root of 2, we'll end with the 3 minus the square root of 2. And then if you were in my class, you know how I like to do my work for my numerator. So here's my work for my numerator. So first, 5 is going to distribute. So 5 times 3 is 15. And then when I multiply 5 with the square root of 2, those are not similar enough. I can't make it 10 or the square root of 10. So it's just going to be 5 times the square root of 2. And now I'm going to go to my denominator, and what I want to do here is not spend all this time with all this multiplying like I did in this example here. Instead, what I want to do, as far as the shortcut goes, and I'm going to erase all these loops here so you see that, is the only loops that matter are the first ones and the last ones. First and last, first and last, because if you do the other ones, that's where all this canceling out happens. See how I'm scribbling that out? So what I'm going to do to save myself a little time is I'm going to multiply the first ones. So here's my denominator. 3 and 3 is 9, and multiply the last ones. So square root of 2 times square root of 2, which is the square root of 4. There's that minus sign that should go in between them. And then the square root of 4 is a nice number, it's 2, and then my denominator can actually end up being 7. So when I'm done, I've got my final numerator and my final denominator. And now this is much better than what we started with, right? Doesn't it look better? But anyway, it doesn't, but that's still the rule we have to follow. So let's take a look at the next one. So again, the problem we have is this radical in the denominator. So to fix that, I'm going to multiply it by its conjugate. So if I start with 4 plus square root of 10, I'll use 4 minus square root of 10. And whatever you do to the bottom, you do to the top. And so first I'll take care of my numerator work. So negative 2 is going to distribute for 4 for negative 8. And when negative 2 distributes to this, the negative and the subtraction can turn into positive. But 2 and square root of 10 cannot become 20. They're not alike enough. So we'll just write it as 2 square root of 10. And now for my denominator, again, I don't need for all of these to multiply. I just need the first set and the last set. And I'll remember that it's just connected with the subtraction sign. So 4 times 4 is 16, and square root of 10 times square root of 10, it's hooked with subtraction, is the square root of 100. And then that just becomes a 10, and when I'm done, my denominator is 6, and then I can make my final numerator over my final denominator. And that's the last one. So at this point, if you don't want to hear about the exponent rules, go ahead and shut this video off. But if you just want to hear them, I'll go ahead and continue. So the two big ones are these two. And it just says if you're multiplying exponents with the same base, that to shorten the problem up even more, you can just add the exponents. So a good example of that would be if I had and I'll be doing some erasing as I go through this, 2 to the third times 2 to the fourth, I'll end up with 2 to the seventh. And the reason why that works is this 2 to the third means I have 3 2's, and this 2 to the fourth means I'm multiplying 2 4 times. And so when I look, I'm multiplying for a total of 7 times. So that's one shortcut. Shortcuts are great, but they're not 100% necessary. So the next one says if I'm dividing with the same base, I can subtract the exponents. So if I have 2 to the fourth over 2 to the third, again, this means 2 is multiplied 4 times. This means 2 is multiplied 3 times. And then what can happen is these 2's can start to cancel each other out. So I'm left with 1 2 in the numerator. So my final answer would be 2. Now, it is possible that when you do this, maybe you have your larger amount of 2's in the denominator and your fewer amount in the numerator. So again, 3 2's on top, 5 in the bottom, and if you cancel them out, I'm left with 2, but I'm left with 2 of them in the denominator. So the rule that I tell my students is go ahead and subtract your exponents. Subtract 4, subtract 3, subtract 3 and 5. And subtract them the easiest way. Do 4 minus 3, do 5 minus 3. And then look at where should your extra 2's have ended up. In the first example, since I started out with more 2's in the numerator, that's where my answer should end up. And then over here, since I ended up or started with more 2's in the denominator, that's where the extra 2's should end up. All right, I'm going to do a little erasing here because I don't have a lot of space to work with. So the next rule I discussed earlier is anything to a 0 power is 1, anything to the first power is itself. And I also talked about that negative exponents do not make things negative, they just move them. So if you start with 3 to the negative 4th power, it just moves into the denominator, and now it's 1 over 3 to the 4th power. But it is possible that you could start with your negative exponent in the denominator, and then it says just move it to the numerator. And once it moves, it's no longer negative. The exponent's no longer negative. So that goes over these two here. And then the final two rules are, what if you have an exponent to another exponent? So instead of using a number this time, I'm going to use letters. So let's do x to the second power and x to the third power. So this 3 here means I have 3 of these x squareds. And then those x squareds are each 2x's and another 2x's and another 2x's. So when I look, I have a total of 6 x's. And what this rule says is you can actually just distribute that in, multiply them, 3 times 2, and get your 6. And then this rule just says if you have a couple things in here, that it would just distribute to each of them. So if I had like 3 to the first power and x to the 4th power and all of that was to the 3rd power, that 3rd power can distribute to the different exponents, and I'd get 3 to the 3rd power and x to the 12th power. So that's just an exponent review. If you listen, good job. And that is it for 3.4 notes.